All right. Hello, everyone. Today is May 10th, Monday. This is Monday evening. I'm taking the lecture video for the 11th week. Hope you guys had a great weekend, stay healthy, and doing well. So now we are approaching the end of the semester. So it's already 11th week after the opening day of the new semester. All right. So in the previous week, we talked about two transcendental functions, natural exponential and logarithmic functions. And we also talked about how to take the derivative, right? So e to the power x, natural exponential function, and the natural logarithm, ln x. Yeah, so that is a logarithm with a base e of x. Yeah. So remarkably, these two transcendental functions have very simple derivatives. So e to the x is its own derivative. So the derivative of e to the x is itself. It does not change at all. But for natural logarithm, the derivative is d ln x over dx is the reciprocal, 1 over x. Okay. So now in this video, what I'm going to do, I'm going to illustrate how this fact, so the derivative of natural logarithm is the reciprocal, is applied to economic problems, okay? So, so you're going to see, why this natural logarithm is widely applied to economics. So you're going to see that is related to, so the derivative of natural logarithm is related to, so that can be used to measure the growth rate of some variable. Okay. So if we are concerned about the growth rate of interest rate, or concerned about one nation's GDP, or the growth rate of some demographic feature like a population or something, whatever. Okay. Whenever we are interested in growth rate of some variable, we have to adopt this natural logarithm, and we should be able to deal with the derivative of a natural logarithm. Yeah. So now, in the subsequent two examples, let me show you how the derivative of a natural logarithm is applied to economic problems. So the first application is taken from the textbook. So there is one problem about wine storage in the textbook. So let me state the problem first. So we have one wine dealer. So wine dealer has a particular quantity of wine, and its current value is k dollars. Okay, but its value in t years follows the natural exponential function. So here v of t measures the value of wine in t years. Okay, so that is given by k times e to the power square root of t. So remember, number e is an irrational number between 2 and 3. So this is an exponential function with a base larger than 1. So that is an increasing function. Although we take the square root on the exponent, does not matter. Square root of t also increasing, but the growth rate is a little bit, so the growth rate is a little bit lower than linear function, but still increasing. Okay, so you can see that if someone matures wine, the value of wine is increasing over time. Yeah, so that increasing rate is captured by this exponential function, natural exponential function. Okay, so what we are going to consider in this situation is dealer has two options. So the dealer may sell the whole wine right now at time 0 at the price of k dollars. Okay, so its current value. So the current market price is given by k. Yeah, or she can wait. Okay, so she can mature the wine and sell in t years at the price of v of t. Yeah. So if we think about what is the optimal timing for the wine dealer, so when is the optimal time so that maximizes the sales revenue? Then we have to compare these two. Which one is larger? So she has to sell right now or she has to wait. Okay? But when we compare these two values, remember that this K or this cash flow occurs right now. If she sells right now, she can earn K dollars right now. Okay? But this V of T, that occurs in T years. So even if she decides to sell in T years, right? This V of T occurs in T years, right? So in order to compare these two guys, we have to take the present value of V of T because this cash flow is occurs in time it occurs in T years. So we have to take the present value operator. But the way to calculate present value is we can simply multiply by e to the power negative RT. So I discussed this, the relevant issue, I guess in the previous week. So when I explained the continuous compounding, so if the interest is compounded continuously, so every second interest is added to your bank account, and then the interest is paid to you, then the present value of K dollars in T years. So if this K dollars cash flow occurs in T years, not right now, but in T years, then the way to convert these K dollars into the present value is, in case of continuous compounding, we can simply multiply by e to the power negative RT, because this present value operator, the limit of this operator as n goes to infinity, n stands for the number of compounding per year. So in case of continuous compounding, we have to take the limit as n goes to infinity. So this guy converges to e to the power negative RT. So that can be regarded as present value operator, the present value converter in case of continuous compounding. So I'm going to use that fact to calculate the present value of V of t. Okay? So the way to convert this future value into the present value, we can simply multiply by e to the power negative RT. Okay? So we come up with a multiplication of two exponential functions, but the base is the same. The base is given by number e. So the multiplication in that case becomes addition, right? So we can simply combine these two exponents. So the present value is going to be k e to the power square root of t minus rt. Okay. R was the annual interest rate. Okay, so take that annual interest as a one parameter. Then we have a one revenue function. So present value of revenue, future revenue. And let me call that A of t. Okay. Now we are thinking of, so we come up with one optimization problem because now we are considering what is the optimal value? What is a optimal timing for sale? So when this value, future value, so the revenue of the present value of the future revenue will be maximized. So now we are gonna solve this optimization problem, max of A of t over time t. Okay? That can be thought of as a so optimization problem for time t. So now we are solving this maximization problem. So when is the best time for this wine dealer to sell for wine? Okay. All right. So now let me adopt a first or second derivative test. So now we are going to adopt a first or second derivative test to solve this optimization problem. So the starting point is we have to take the derivative, right? So to find the first of the condition. So we are going to take the derivative of a with respect to time t. Now the choice variable is time t. Okay, and then we already convert the objective function that we want to maximize as a function of time t. So now we are ready to take the derivative and set it equal to 0 to find the critical point of the function a. Okay, so function a is given here. Then the way to find the derivative is, the best way to find the derivative is, let me use logarithmic differentiation. So take the natural logarithm of both sides, ln a of t and ln this expression. Okay. Okay. So what we are looking for is dA over dt. Okay. So after taking natural logarithm, we take the derivative of both sides with respect to time t. Yeah. Then the expression on the left side, ln of a of t, that is a composite function of ln and a of t. So the outer function is ln and the inner function is a of t. Okay, so using the chain rule, the derivative of the outer function, that is 1 over a of t. So ln a of t is a composite function of, say, f of g of t. Outer function f is ln, say, t. And inner function g of t is a of t. Okay? So by the chain rule, the way to take the derivative of a composite function is we first consider, so we first take the derivative of the outer function, so f prime. The derivative of ln t is a reciprocal. Yeah, so we have 1 over a of t. And then we multiply by the derivative of the inner function. So dA over dt. Yeah, that is what we are looking for. Right? And then the right side, before take the derivative, now let me use the rule of logarithm to simplify this expression. So ln of k e to the power square root of t minus rt. Okay. So in natural logarithm, multiplication becomes addition. So ln k plus ln e square root of t minus rt. Yeah. And then ln k is a constant. Okay. And then ln, natural logarithm, is defined as the inverse function of exponential function, natural exponential function. So ln and e are cancelled off. So we are going to left with just the exponent. Okay. So now we take the derivative with respect to time t. So k is a constant, so that this guy goes away. And square root of t's derivative is 1 over 2 square root of t, and minus rt becomes minus r. Okay. So dA over dt is a of t times 1 over 2 square root of t minus r. So by multiplying by a of t, so multiplying both sides by a of t, we obtain this. Then a of t is the present value of future revenue, so k 1 over 2 minus r. Alright, so we obtain the derivative. We obtain the expression of the derivative using logarithmic differentiation. Right? And then we set it equal to 0. We set it equal to 0. Okay? And remember, also, if we think about how to express it, so how to make this expression be equal to 0. Remember, the exponential function is always positive. No matter what the exponent, it never touches the horizontal axis. It is always above the horizontal axis. So there is no chance that this guy, the first term, is equal to 0. Okay? So the only way to make this expression be equal to 0, in order to have 0 from this expression, this guy, the expression in the parentheses should be equal to 0. Okay? So the first of the condition can be simplified to 1 over 2 square root of t minus equals r. So if we solve this for t, then we obtain square root of t equals 1 over 2r. So t should be 1 over 4 r squared. Yeah. So the function a of t has a unique critical point at this point. Okay. So when t equals 1 over 4 r squared. Right. So here, so this diagram shows that determination of the critical point. So this curve is the graph of 1 over 2 square root of t. Okay. So the critical point t star is determined at the intersection where where this curve meets the horizontal line r. Okay. So t star, the critical point t star, is determined by this equation. Right. So if we think about the intuition, so why the critical point is determined at this point? So the intuition is behind. So the intuition behind is so we can interpret this 1 over 2 square root of t as the rate of growth of y value. Okay? And if we think about the growth rate, so growth rate of something, growth rate, that is a percentage change. Okay? So if some variable x, originally that was x, or 100, right? And then that increases to x prime, say 110, right? Then growth rate is 10%. The way to find this percentage change is we compute change in x and then divide it by the original value of x, the previous value of x, right? So in terms of differential, we can write this dx over x, right? So if we consider marginal change in x, suppose that x changes marginally, say from 100 to 101. Okay, so changes by 1%. Okay? So whenever we consider marginal change, the growth rate can be expressed as dx over x. Okay, but remember, the d ln x over dx. The derivative of the natural logarithm is 1 over x. Okay? So if we multiply both sides by dx, then dx canceled on the left hand side. So we are left with d ln x. That is a log differential of x. And then on the right side, we have dx over x. Okay? So growth rate of variable x is equal to log differential. This is called log differential. Okay? So the y value in t years for e of t was given by k e to the square root of t. Right? And then if we think about the growth rate of value, and we take the logarithm, so ln k plus square root of t, yeah, because ln k e to the square root of t equals ln k plus ln e to the power square root of t. And once again, ln and e have an inverse relationship. So these two are canceled. Whenever they meet, they are canceled. Okay? So we are left with square root of t. So now we take the differential. d ln v of t is, this is a constant. So the differential for a constant is 0. It does not change at all. Okay? And then the differential of a square root of t is derivative times dt. Okay, so from that, we can infer 1 over square root of 2t. Okay, that is the growth rate of the value, the growth rate of y value. Okay, so this curve shows the growth rate of y value at time t. Okay, and then r, that is the interest rate. Okay, so interest rate can be thought of as an opportunity cost of waiting. If you wait, then the revenue is realized later. So you can lose the earned interest. Okay? So interpreting R as an opportunity cost, and then interpreting this growth rate as a benefit, as a marginal value of waiting, marginal benefit from waiting. Okay? So the optimal timing is determined at this point where marginal value, marginal benefit from waiting is equal to uh, opportunity cost. Okay. All right. So critical point is determined at this point where marginal benefit is equal to marginal cost. Okay, so the coordinate of the point is 1 over 4 r squared. Okay? But this is not the end of the story because now we are trying to solve this maximization problem, but first the condition is just a necessary condition. Okay, so we have to check. So using the second derivative test, we have to verify the second derivative has a negative value at this critical point. Okay, so we have to compute the second derivative, right? But the first derivative was right here. dA over dt is a over t times this expression. Okay, and using that, let me compute the second derivative. So the derivative of the derivative. Yeah, but the derivative is a product of two functions. So using the product rule, we first take the derivative of the first function. That gives me dA over dt. Okay, and then multiply by the second function and plus, leave the first function alone, and then multiply by the derivative of the second. Negative r, that is a constant, is not a function of time t, so it goes away. And 1 over 2 square root of t, whose derivative is minus, so negative 1 over 4 t to the power negative 3 halves. Okay, because think about 1 over t's derivative. That is, so 1 over square root of t is t to the power negative 1 half. Okay, square root of t is t to the power 1 half. And its reciprocal is just a negative exponent. So 1 over square root of t is a t to the power negative 1 half. Now we are computing the derivative. So using the power negative 1 half comes up front. And then we take 1 away from the power. So the new power becomes negative 3 over 2. Okay? So we have additional 1 half in front. So the derivative becomes this guy times 1 half. So we have negative 1/4. Yeah, negative 1/4 t to the power 3 halves. All right, so we have this. And then we have to examine the sign of this guy at the critical point. So at t equals 1 over 4 r squared. Okay, so that was our candidate for the solution to the optimization problem. So we have to check the sign of this at this critical point. Okay? If that is a negative at this critical point, the function a of t has a local maximum. And if the sign is a positive, the function has a relative minimum. Okay? All right, so when t equals 1 over 4 r squared, observe that this guy is equal to 0. Yeah. So no matter what the derivative, the first term goes away. So if we substitute this expression for t, you're gonna have, so this expression in the parentheses goes away. Because that was the first order condition. We derived this critical point from this equation. Right? So at that point, r should be equal to 1 over 2 square root of t. So that guy goes away. Okay? And then you substitute that expression for t right here. Okay? So that is some value, positive value, minus 1/4. Okay? So this guy is a negative, and a of t, that is an exponential function, always positive. So the product of positive value and negative value, that is a negative. So we can make sure second derivative is a negative. Yeah? Because the first term goes away, so we don't have to care about the first term. Okay? The sign of the second depends on the sign of the second term. A of t is always positive. And we have a negative 1/4, and t to the power negative 3/2, that is a positive value. So we have a negative second derivative. So we can make sure the function, so the function is initially increasing and then starts decreasing. Yeah. So at this critical point, where is the critical point? Yeah. At this critical point, the function attains global maximum. Okay. Think about the sign of the derivative. Whenever t is lower than this guy, if t is a small number, because we have t on the bottom, so when t is a small number, this guy will be a large number. So the derivative is a positive. It means the derivative starts increasing when t is low and after hitting the maximum. So when t equals this critical point, hitting the maximum, and then now t is larger than this guy. So now this fraction becomes lower and lower. It is getting smaller and smaller. So now the derivative will take the negative sign. So it starts decreasing. Yeah. All right. So I think I'm done with the first application. And the second application is essentially in the same line with the first application. So I already explained the punchline of the, why the derivative of a natural logarithm is widely applied to economics. It is used to measure percentage change. Okay, so using that idea, if we revisit price elasticity of demand, okay, that was defined as percentage change in quantity, so quantity demanded divided by percentage change in price. Okay, so it can be thought of as the growth rate of quantity demanded divided by growth rate of price. Okay, so in other words, dq over q divided by dp over p. Okay, and remember, percentage change in some variable, so growth rate, can be expressed as its log differential. So d ln q over dq, the derivative of a natural logarithm, is equal to reciprocal. So from that, we obtain d ln q equals dq over q. Okay? So the growth rate of variable q, in other words, percentage change in q, can be expressed as log differential. Okay, so using the same idea, we can define elasticity as d ln q over d ln p. All right. So the ratio of two log differentials. Yeah. So now using this new formula, let me compute price elasticity given this market demand function. So using this now, Q is given by quantity demanded given by K over P. And K is a some constant, positive constant. Okay. Remember, elasticity is defined as d ln Q over d ln P. Okay. So we have to find these two log differentials. But let me first take the logarithm. So ln Q equals ln K over P. And using the property of natural logarithm, I can rewrite the right-hand side ln K minus ln P. Right? Division becomes difference. Right? And then let me relabel ln Q by q small q and ln P small p. Relabel by q. Okay. So then it gives me q, small q equals ln K minus small p. Okay. And then finding total differential. Then q becomes dq. K is a constant, so it goes away. And p becomes negative dp. All right. Now substituting back the ln q and ln p, we obtain d ln q equals minus d ln p. So dividing both sides by d ln p, d ln q divided by d ln p gives me negative 1. Okay. So that is the way to compute price elasticity in a much simpler way, much more simple way, okay? Using a log differential. So it turns out that if the demand function follows this hyperbola, price elasticity is always equal to 1. Okay? We usually put the negative sign in front, so elasticity is defined by minus this guy, negative of this guy. So we have positive 1. So that means whenever demand function follows hyperbola, we have, so demand is unit elastic at every point. Okay, so in this video, I illustrated how the derivative of a natural logarithm is used to economic problems. So the punchline of this video is growth rate of something, some variable, can be expressed as, where is the, so can be expressed as the growth rate of something is equivalent to, so it's the same as a log differential, right? So I hope you guys enjoyed this video, and I'll see you guys in the next one.